So in the last class, we have seen a number of preemptive CPU scheduling, and in the preemptive CPU scheduling, we have seen that particularly two of the non-preemptive schedulers, that is the priority scheduler and the shortest job first scheduler, they can be modified to make them preemptive. Okay, and when the shortest job first type of scheduling is modified to become a preemptive scheduling, we have seen that this becomes a shortest remaining time first scheduling technique. That is, at any point of time when the CPU has to be given a new job, we just determine from the ready queue a job for which the remaining time of a CPU burst is minimum. Okay, so the job for which the remaining time of a CPU burst is minimum, that job is allocated to the CPU for execution. Okay, so this becomes a preemptive scheduling technique in the sense that any time, whenever it is needed, we can forcibly terminate the job that is being currently executed by the CPU and give a new job to the CPU for execution. Okay, now let us see another kind of CPU scheduling technique, which is again a preemptive one, and that is called a round robin scheduling. In round robin scheduling, what we do is we don't make any decision based upon what is the CPU burst time required for the job or what is the priority of the job. All the jobs are treated equally. Okay. In this case, what you do is the CPU time is divided into a number of quanta. So I can assume that a CPU quanta may be of duration, say, 2 milliseconds. Okay. So whenever a job is to be allocated to the CPU for execution, it will be allocated or it will be executed for a maximum of 2 milliseconds. Okay. If the CPU burst time required for the job is more than 2 milliseconds, after 2 milliseconds, the job will be forcibly terminated. It will be pushed back into the ready queue, okay, and a new job from the ready queue will be allocated to the CPU for execution. And again, that will be executed for a quantum of 2 milliseconds. Okay. In case the CPU burst requirement of the job is less than 2 milliseconds, in that case, the job will be terminated automatically. It is not a forcible termination. Okay. So after termination of that CPU burst of the job, which is less than 2 milliseconds, the job may either go to halted state, the job may be complete, or it may go to an IO waiting state when the job will wait for an IO operation. Okay. And what happens to the CPU? Suppose my job requires a CPU burst time of 1 millisecond, whereas the quanta time is 2 milliseconds. Okay. But the CPU cannot remain idle for that remaining 1 millisecond. So what happens is, whenever the job is terminated on its own, a new job will be allocated to the CPU for execution, and the next quanta will start from that point onwards. Okay. So I have a situation like this. Coming back to a similar example, suppose I have job J1, job J2, J3, J4. Job J1, let us assume it takes 4 milliseconds. Job J2, let us assume it takes 2 milliseconds. Job J3 may take 3 milliseconds. And job J4 may take 6 milliseconds. Okay. Now let us see how that round robin scheduling will work on this sequence of jobs. Our assumption is that the CPU time quanta is 2 milliseconds. Okay. Now from these jobs, the jobs will be taken over first time in the first come first served basis. So job J1, which is at the head of the queue, it will be taken up for execution, and it will be executed for a period of 2 milliseconds. So this is the period during which job J1 will be executed. After this 2 millisecond quanta, because one quanta is complete, job J1 will be forcibly terminated, though its CPU burst is not yet complete. The CPU burst time requirement is 4 milliseconds, but it has been executed for 2 milliseconds. Okay? So after 2 milliseconds, job J1 will be terminated. It will be pushed back into the ready queue with the remaining CPU burst time of 2 milliseconds. Okay. Then the CPU will be given to job J2. J2 will again be executed for 2 milliseconds. Okay. And you find that here the CPU burst time requirement of job J2 was also 2 milliseconds. That means this job, the CPU burst requirement of this job J2 is complete. So at the end of this, job J2 will either move into the halted state, that is the entire lifetime of job J2 is complete, or job J2 may be moved into the IO waiting state if at the end of this CPU burst, job J2 needs any IO operation. Okay. And from that IO waiting state, once that IO operation is complete, again it will go back to ready state. Okay. Now after that comes job J3, whose time requirement, the CPU burst is 3 milliseconds, but it will be executed for 2 milliseconds. Okay. So now you execute job J3 for 2 milliseconds. At the end of these 2 milliseconds, again job J3 will be pushed back into the ready queue for remaining CPU burst of 1 millisecond. Okay. After that, job J4 will be executed, whose time requirement is 6 milliseconds. It will be executed for 2 milliseconds. Okay.
This is all happening in the first come, first served basis?
First come, first served basis. The way it has appeared in the ready queue. I always take the job from the head of the ready queue, give it to the CPU for execution, and it will be executed for a maximum of 1 time quanta. Okay. So with this job J4, having completed 1 quanta, now again I go back to job J1. Okay. Assuming that job J2 is still in the, either it has become halted, that is its lifetime is over, or job J2 is still waiting in the IO waiting state. Okay. Now in case job J2 completes the IO operation in between and comes back to the ready queue, the time when job J2 will be taken up for execution, that depends upon in which position in the ready queue job J2 has appeared. So when I come to the ready queue, I always take the job from the head of the ready queue. Okay. And the jobs are pushed into the ready queue depending upon their time of arrival. This arrival may be from the new state, the arrival from the maybe from the IO waiting state, or arrival may also be from the active state in case of forcible termination. So here you find that with the help of this process state diagram that we have discussed in the last class, that there are 3 incoming paths to ready state. One is from the new state, one from the active state, one from the waiting state. So a job may come to ready state from any of these different states. Okay. And depending upon the relative order in which they are coming, the relative order in the ready queue will be different. Okay. However, for this round robin scheduling, we'll always take up a job for execution from the head of the ready queue. Okay. So after job J4 has completed 1 time quanta, I come back to job J1 because this is moving in a circular direction. Job J1 is waiting for its remaining CPU burst of 1 time quanta. So job J1 will be completed. It completes the remaining time quanta. Then comes to job J3, which is waiting for remaining CPU burst of 1 millisecond. Because out of 3 milliseconds, 2 milliseconds is already complete. So job J3 will be executed for 1 millisecond, and after that job J4 will be taken up for execution. And job J4 is in the ready queue for a remaining CPU burst time of 4 milliseconds. Okay. Out of that, initially 2 milliseconds will be given to job J4. So here you find that our time quanta starts at this point when job J3 was complete. So this amount of time was for 1 millisecond, and the next 2 millisecond quanta starts from here. Right? So after completion of 2 milliseconds of the remaining CPU burst time of job J4, if I assume that there is no other job which has arrived in the ready queue in between, I have only one job that is left in the ready queue, that is job J4, and which is waiting for its remaining CPU burst of another 2 milliseconds. Okay? So job J4 will be executed again for the remaining 2 milliseconds, and after that you find that all the CPU bursts of all the jobs in the ready queue is complete. Okay. So this is how the round robin scheduling will work. And here you find that I didn't give any priority to any of the jobs, neither to a job which requires minimum CPU burst time, neither to a job which has been set to a higher priority by either the user or the administrator. Okay. So all the jobs are treated equally in round robin scheduling. Now, when I go for this round robin scheduling, you must have noticed that I must have some agent who will tell the CPU that one quanta is over, isn't it? That means I must have some timer. In the system, this timer may be programmable. If I want that for one installation, I mean, that can be specified by the user or the administrator, that in some installation I may want a time quanta of 2 milliseconds. In some other installation, I may want a higher quanta, a quanta maybe of 5 milliseconds. Okay. So this timer, this should be programmable so that the interval at which it will interrupt the processor, that can be varied. Okay. So I must need a programmable timer. Okay. So what has to be done now? Whenever the CPU scheduler decides that a new job has to be allocated to the CPU, or it allocates a new job to the CPU, immediately the timer has to be reset. Okay. Then at the end of the time quanta, the timer will generate an interrupt when again the CPU will go to the system's program, and the responsibility of that system's program will be terminate the currently executed job, get a new job from the ready queue, give it to the CPU for execution, and restart the timer. Right? So that is what will happen in case the CPU burst time, required CPU burst time, is more than the time quanta as set in the timer. If the CPU burst time is less than that, in that case, the process is not executed till the timer gives an interrupt. The execution is complete before the timer interrupt comes. Okay. So the last statement of every CPU burst must be a system call. Okay, the system call for performing an IO operation, or system call indicating that the process is complete. Okay. So again, following that system call, you have to get a new process from the ready queue, give it to the CPU for execution, and at the same time the timer has to be reset so that the next time quanta starts from that point onwards. Okay. So this is the simple round robin scheduling that we can have. Okay. Now we can have different variations of this round robin scheduling. For example, as we have said, that here I have not put any consideration regarding the nature of the job, but we have discussed in our last lecture that the jobs may be of two kinds. Either the job needs more of CPU time and less of IO operation, in which case the job is a CPU bound job. In the second category, I can have jobs which needs more of I/O operation and less of CPU time. That means the CPU burst duration for an I/O bound job is very, very short. Okay. And as we have seen that in the shortest job first scheduling or shortest remaining time scheduling, I get an advantage that the average waiting time is reduced. Okay. So I can think whether I can incorporate the same advantage in this round robin scheduling also. That means my basic scheduling technique will be round robin scheduling. In addition to that, I also want to get an advantage which otherwise I get in shortest job first scheduling. Okay. So how to do it? And if I can do that, then though I will have round robin scheduling, even then I can prefer the jobs which require less CPU time. Okay. So all the I/O bound jobs will get preference of over the CPU bound jobs, because CPU bound jobs require more of CPU time and I/O bound jobs require less of CPU time. Okay. So let us see how that can be done. Okay. Now before coming to the proper implementation, there is another concept which is called a multi-level queue scheduling. So you can have a multi-level queue. I think yesterday somebody was asking me whether we can have multiple queues instead of a single queue. Okay, so here comes the multi-level queue. If we can categorize the jobs depending upon its CPU time requirement, then what I can do is, instead of having a single ready queue, I can have multiple ready queues. Okay, so I'll put multiple ready queues like this. So this is one ready queue. This may be another ready queue. And here I can have another ready queue. So suppose I categorize the jobs in 3 different categories. Okay. The first ready queue will contain the jobs, let us say, whose CPU burst duration is less than or equal to 2 milliseconds. Okay. The second ready queue may be containing the jobs whose CPU burst requirement is greater than 2 milliseconds but less than 5 milliseconds. Okay. So this will contain all the jobs whose CPU time requirement is greater than 2 milliseconds but less than or equal to 5 milliseconds. And this may contain the jobs whose CPU time requirement is greater than 5 milliseconds. Or burst duration is greater than 5 milliseconds. So if by some means we can estimate that what is the average CPU burst time of the job, I can put the job in one of the ready queues. Okay. And here our assumption will be that because the first queue, say Q1, which contains the jobs whose CPU time requirement is less, every CPU burst is less than or equal to 2 milliseconds. So I can consider those are the shorter jobs or I/O bound jobs which should get preference over the CPU bound jobs. In Q2, the CPU bursts are moderately short. It is not as short as these jobs, but the CPU time requirement is greater than the CPU time requirement of these jobs. So I put those jobs in Q2. And all the jobs which are strictly CPU bound, that means every CPU burst is greater than 5 milliseconds. Okay, I put them in queue number 3. Okay. Now what I can do is, I can apply round robin scheduling on each of these queues separately. But what I'll do is, I will take a job from queue number Q2 for execution only when queue number 1 is empty. That means, if I have a job in queue number 1, that will be executed first. When all the jobs in queue number 2 are complete, queue number 1 are complete, then only I'll take up jobs from queue number 2 for execution. That gives higher preference of the IO bound jobs for execution on the CPU. Okay? Similarly, when I come to queue number 3, I will ensure that the jobs in queue number 1 and queue number 2, they are complete. That means both queue number 1 and queue number 2, they are empty. Only in that case, I'll take up a job from queue number 3 for execution. Okay. So the jobs in queue number 3 will have the least priority. Jobs in queue number 1 will have the highest priority. Okay. But there is a disadvantage. It does not take care of the dynamic nature of the job. Okay. So for example, if a job initially, it may take CPU bursts of greater than 5 milliseconds. Okay. That means the job is CPU bound. But after some time, maybe the job becomes IO bound. That means the CPU time requirement of the job will be less. Okay. Similarly, a job which initially was IO bound, that is the CPU burst of the jobs was less than 2 milliseconds, right? After some time, the job may be CPU bound. That is, the CPU burst requirement of the job will become greater than 2 milliseconds.
So how can we predict the CPU burst before execution?
Pardon?
How can we predict CPU burst time?
How can you
Predict. How can we guess the CPU burst?
First time it is first come first serve. Then you have to use that prediction formula. First time it is first come first serve.
So, average CPU burst time can't be calculated in that case. Average CPU burst.
No, what I am saying is, if the nature of the job is dynamic, okay, even the prediction will work, but the prediction will have some latency. Okay. So in this multi-level queue, our assumption is, if initially I can say that the job is CPU bound, I'll put that job into queue number 3 and it will remain in queue number 3 for its entire lifetime. If initially I can find out that the job is IO bound, it will be put in queue number 1 and it will remain in queue number 1 for its entire lifetime. But maybe in between, the job which was put in queue number 1, that has become a CPU bound job. But still it will keep on getting preference because I didn't keep any provision for considering the dynamic nature of the job. Okay. So that can be done by modifying this multi-level queue to what is called a multi-level feedback queue. Okay. So what we can have is a multi-level feedback queue. Okay. So what I will do in multi-level feedback queue, again I will have multiple number of queues. So let us assume as before that I have 3 queues. Like this, but now with the provision that I can move the job from one queue to another queue. Okay. Whenever a job enters the system for the first time, the job is always put in queue number 1. So this is Q1. This is Q2. This is Q3. Okay. As before, I will set time quanta for Q number 1 to be 2 milliseconds. Time quanta for Q number 2 may be 5 milliseconds. Time quanta for Q number 3 is more than that. I can make it, say, 10 milliseconds. Okay. So whenever a job enters the system for the first time, let me assume I don't know what is the nature of the job, whether the job is CPU bound or whether the job is IO bound, or what will be the CPU burst duration of the job. I don't know anything. I simply put that into queue number 1. In queue number 1, the job will be allocated to the CPU for execution following round robin scheduling technique. Okay. Now, once it is allocated to the CPU, it will be executed for a minimum of 2 millisecond time period. Right? If I find that the CPU burst of the job is over before that 2 millisecond duration, I will keep the job in queue number 1 only. I will not move the job. Okay? Because the first time it has executed, it has shown that the CPU burst requirement is less than 2 milliseconds. So I assume, again my prediction, that the next CPU burst time will also be less than 2 milliseconds. So I don't need even a prediction formula. I am just keeping a threshold that whether it is less than 2 milliseconds or greater than 2 milliseconds. Right? So if the CPU burst of the job is less than 2 milliseconds, that means that the CPU burst of the job is complete before the timer interrupt comes. 2 millisecond timer interrupt comes, the job remains in queue number 1. Okay. If the CPU burst of the job is greater than 2 milliseconds, that means even when the timer interrupt has occurred, the CPU burst of the job was not complete. Okay. So if the burst is greater than 2 milliseconds, I will push the job into this next queue whose quanta size is 5 milliseconds. Okay. And again, in queue number 2, it will be allocated to the CPU for a time quanta of 5 milliseconds, again following round robin technique. Okay. In queue number 2, if I find that the CPU time requirement of a job is less than 5 milliseconds, it will remain in this queue only. If the CPU burst duration of the job is greater than 5 milliseconds, I will push the job into the last queue, that is queue number 3, where the time quanta is 10 milliseconds. Okay. In each of these queues, the jobs will be allocated in round robin fashion. Right? So first time when a job enters the system, you push that into the first queue. If the time quanta is, if the CPU burst time is less than 2 milliseconds, you retain the job in first queue only. Don't move it. If the time quanta is greater than 2 milliseconds, then I know that it is not an IO bound job. I push it downwards gradually depending upon the nature of the job. I can also have one provision that in the last queue, if I find that the time quanta of the job is less than 5 milliseconds, okay, I should be able to push it up, which gives me full freedom. That means if the job is at during some duration of time remains to be IO bound, it will remain in queue number 1. Whenever it changes its nature from IO bound to CPU bound, I push it downwards. That means I start giving it lower preference. Similarly, at the bottom queue, as long as the job is CPU bound, it will remain in the queue number 3 where the priority is less. Whenever the job changes its nature, that is, it starts becoming IO bound, I start pushing it upwards. When I push it upwards, that means I am increasing its priority. So here again, queue number 1 will have highest priority, queue number 2 will have lower priority, and queue number 3 will have the lowest priority among these 3. Okay? So you find that if I go for this multi-level feedback queue, I can find out the dynamic nature of the job and put the job in the appropriate queue based on its nature. Right? So this is a variation of the round robin scheduling technique, or a modification of the multi-level queue technique, where I can schedule the job as per its nature.
But we haven't shown the arrows going up.
Pardon?
So we haven't shown the arrows going up, like pushing them up.
Yeah. So what I said, that this is option. I can have this provision. But at the cost of what? I must incur some cost for this. See, so far as pushing down is concerned, it is very simple. Okay. At the timer interval, I just check whether there is still more time left for that job or not. But if I want to push a job upward in the queue, what I have to do is, I have to monitor this 5 millisecond, 10 millisecond, 2 millisecond to find out where to put this job. Okay, so that requires some extra processing. Right? So that is why this upward pushing is normally not used, though it can be done.
So instead of pushing it backwards, why can't you push it to again 2 milliseconds, so that if that requires more than 2 milliseconds, it will again come to 5 milliseconds. So only one backward loop to the first one.
No, what can be done is, it is not only going to this level, I can also make it, say from here, I can also put it to the topmost level.
That one only will suffice, no sir? Because if it requires more than 2 milliseconds, it will again come back to 5 and loop continues.
That is okay, but in that case, you are incurring more and more switchover time. See, whenever you switch over the job from one state to another state, you also have a context switching time. Okay, that will be reduced if I can place this job in the appropriate queue. So I can have both of these. From Q3 to Q2, I can also have Q3 to Q1. Both of these feedback connections may be present. Okay, so in queue number 3, if I can determine that it has executed a CPU burst whose time requirement was less than 2 milliseconds, I'll put it in queue number 1. If I determine that it has completed a CPU burst whose duration was less than 5 milliseconds but greater than 2 milliseconds, I'll put it in queue number 2. Okay, so I can place it in appropriate location, but I have to have some extra processing for that. So that is the reason that this feedback connection is normally not used. Only what we have is feed forward. Okay.
So we are doing this queue management for future job management. Suppose a job of 3.5 milliseconds comes in Q1,
Yeah.
and after 2 milliseconds we find that there's more time left for it, and we send it to the lower priority queue. But there's only 1.5 millisecond left for that particular job. So ideally it should have been in Q1.
But I don't know that what is the time remaining. I just know that how much time has been elapsed.
So then, how does this architecture, serve your purpose? Because ultimately we are pushing a high priority job to a low priority queue.
No, if it is 3.5, it should remain in queue number 2.
But I have already done 2 millisecond amount of work.
That is for the current CPU burst. What about the next CPU burst?
That is 1.5.
That is not the next CPU burst. That is the remaining time of the current CPU burst. The CPU burst is 3.5. Out of which 2 milliseconds has been executed in queue number 1. For remaining 1.5 millisecond, for that CPU burst, it will be executed in queue number 2. Okay. But the future CPU bursts will get proper attention.
We assume that these CPU bursts are uniformly placed. They are of the same nature.
At least over a short interval of time. Over a short period of time.
Sir, if this Q1 is never empty, means jobs are always coming to Q1,
Yeah.
then jobs will not be performed.
Yeah, again, then what can be used is you can go for the aging concept that we have said in case of priority scheduling.
Sir, at that condition, so why can't we put it forward in queue number 2? In case of the 3.5 millisecond job. So So in that case,
you think of the answer. It is very simple. Okay? So this is about the multi-level feedback queue that we can have. Okay. So we have discussed about various CPU scheduling techniques. Of course, the simplest CPU scheduling technique that we have discussed is the first come first serve, FCFS. Then we have talked about the shortest job first CPU scheduling technique. Then we have talked about the priority scheduling technique. And these are non-preemptive. Okay, and among the other category, we have talked about the shortest remaining time first scheduling, SRT, and we have also talked about the round robin scheduling, okay, and we have also talked about the multi-level feedback queue. And these three are preemptive scheduling. Okay? But all these scheduling techniques that we have discussed, we have assumed that I have a single CPU, and that single CPU has to be shared by a number of processes. And how best we can share a single CPU among a number of processes. For that, we have discussed about so many scheduling techniques. What are the different forms of scheduling that we can have? Then, during our introductory lecture, I have mentioned that the modern operating system should not remain satisfied with a single processor unit. Okay? We have to think of multiple processing unit where I have multiple CPU or maybe multiple computers connected over a network, which is called a distributed computing environment. Okay? So today's operating system must consider that distributing computing nature. Okay? So in the distributed environment, what I have is, I have a number of computers connected over a network. So in our case, we will assume that it is a local area network. So this is distributed computing. Okay. So here the situation is different. In earlier case, we had one resource and multiple processes among which the resource is to be shared. Now what we have is, we have multiple resources and multiple requirements. Okay? So in the distributed computing environment, I have a number of computers which are connected over the network. Okay? And I have a number of jobs which are to be executed in that distributed environment. So there my decision has to be that which of the jobs is to be allocated to which of the computers. Okay? So for that, different considerations are to be made. Now when I come to this distributed computing environment, typically I can have two types of environments. Okay? One is called an workstation model. So we have to see that what is the model of the distributed environment. One is called an workstation model. Okay? And the second model is called a processor pool model. Okay. Now, what is the workstation model? If I consider the LAN environment that we have in our institute, here what we have a number of PCs or a number of workstations which are connected over the same LAN. That means every user is having one full-fledged computer, having its own memory, having its own processor, having its own disk. So even if I remove the networking part, the computer is an independent computer. So this is a kind of model which is known as workstation model. That means every user is given a workstation and all the workstations are connected over a LAN. Okay. Now in the second model, that is a processor pool model, what is done is you can have a high-end server having multiple processors. Okay. So in a single server, I can have more than one CPUs, and what is given to the users is a high-end terminal, maybe a graphics terminal. So the user terminals does not have any processing capability. They don't have any disk, they don't have any CPU. The processing has to be done on the server, and the users just have a terminal. The server is having more than one processor. Okay, so find that these two models are different. In the workstation model, every user computer has the processing power. In case of processor pool model, the terminal which is given to the user, that does not have any processing power. The processing power is at a central place where I have a high-end server having multiple number of processors. Okay? So, naturally, for these two types of models, that approach that you have to take for proper sharing of the CPUs have to be different. Okay. Now, when we come to this CPU allocation in this distributed computing environment, we can have two different types of allocation techniques. One of that allocation technique is non-migratory. And the other allocation technique is migratory allocation technique. Now, what is this non-migratory and migratory? We can say that non-migratory is to some extent static in nature. That is, as we have seen, that in case of our non-preemptive scheduling, what we have done is, once a process is given to the CPU for execution, the process has to terminate on its own. It cannot be terminated forcibly. Whereas in case of preemptive scheduling, the process can be terminated forcibly at the end of the time quanta or whenever it is needed. Similarly, in case of non-migratory, whenever you create a process, at the same time you decide that on which of the processors this process should execute. And once it is decided, that is fixed. That process is executed on the allocated processor until it is terminated. Okay. In case of migratory, we can shift a process or migrate a process from one processor to another processor. Okay. So you can say that this non-migratory approach is static, whereas the migratory approach is dynamic. Right? So we'll see more on this in our next class.